developing the National Weather Service in Louisville by joining friends in Skywarn Storm Clouds. This training consists of 4 required modules. A short quiz will follow each module. Once you've completed all of the modules, you'll be able to register in the NWS Louisville Spotter database and will receive a certificate of completion. This module will provide you with a guide to what cloud features to look for that indicate potential severe weather. Other modules include the basics of weather warnings, a description of what the National Weather Service classifies as severe thunderstorms and how we warn the public of them, how the weather works, a brief look at how and why thunderstorms develop, information exchange, where we discuss how you can get information you need to keep yourself and your loved ones safe, and how you can help others by relaying your observations to the National Weather Service. Additional supplemental modules will be made available in the future, and you're encouraged to take as many of these as you'd like. In this module, we'll take a look at several examples of the clouds associated with severe weather. All of these clouds were discussed in the How the Weather Works module. Keep in mind that many times the subtle features that indicate a storm may become severe are masked by other clouds or obstructions that make them difficult to see unless you happen to be in the right place at the right time. As you view the videos, see if you can determine what the name of the cloud feature is before we show you. As with the other modules, there will be a short quiz at the end of this presentation. This video shows us a storm near the famous Churchill Downs racetrack in Louisville. One of the first things you'll notice here is the obvious rotation of the cloud. Even without the sirens wailing in the background, you can see enough here to surmise that this is a rotating wall cloud. The direction of rotation with the wall cloud is significant because more than 95% of all tornadoes rotate cyclonically. Cyclonic rotation is rotation that, when viewed from above, is in the same direction as the rotation of the Earth. In the northern hemisphere, this is counterclockwise. However, since we're looking at it from below and at a distance, cyclonic rotation is indicated when the part of the rotating cloud closest to the observer moves from left to right, while the part of the wall cloud farthest away from the observer moves from right to left. Moments after the end of this video clip, this wall cloud produced an EF2 tornado that touched down on the backside of Churchill Downs and traveled more than a mile eastward, passing just south of the University of Louisville's football stadium. This video is a little trickier than the previous one. Watch for a few moments and see if rotation is evident. If you look closely enough, you can see some rotation in this cloud. You can also see cloud shreds developing and rising quickly on the underside of the main cloud. This indicates rapid upward motion. Rapid upward motion and rotation is a very dangerous combination for a wall cloud, and usually indicates that a tornado is about to touch down.
Oh, listen to it. Oh, man. That's a tornado if I ever... I'm recording it. Oh, my gosh, look at it. No, not yet.
Look at those leaves floating in the road top of us.
Oh, man, that is awesome.
Oh, there it is, tornado.
Oh, my God. Get it out.
Here we go.
Notice that while no visible funnel was observed, the woman recording this tornado saw debris on the ground just to the left of the building and quickly turned to run for cover. This was a tornado. There was a connection between the rotation of the cloud and the rotation stirring up debris on the ground. The F2 tornado eventually displayed a visible funnel along its nearly 10-mile-long path of destruction. Listen closely to the people talking in this video. Especially at a distance, it's not uncommon to mistake dark objects flying through the air as birds, when in fact it's flying debris from a tornado touchdown.
They are birds. Up there, over the trees. There it is. There it is. See it?
EF2 tornado had maximum winds estimated around 120 miles per hour. There should be little doubt as to what we're viewing in this video. Notice once again the flying debris, which could easily be mistaken as birds, especially at a distance. Notice that this tornado is moving from right to left in the video. Since tornadoes follow the direction of the storms, and since most storms move from west to east in the Ohio Valley, this tells us the observer is most likely north of the tornado's path. Recall from our How the Weather Works module that the area north of a supercell tornado is where the heaviest precipitation, in the form of rain and hail, falls. You can see and hear the large hail starting to fall as the tornado continues. And notice near the end of the video how the heavy rain reduces the visibility, making even this giant EF4 tornado difficult to see. Videos we've just witnessed were all associated with supercell thunderstorms. While they all had similar structures aloft, the visible clouds at the bottom of the storms all looked very different, and the tornadoes associated with the storms varied greatly in intensity, as well as time and distance on the ground. These Doppler radar images show two storms that look very similar, crossing nearly the same path, separated by just 13 minutes. It is important to note that while they look similar in both reflectivity and velocity, the first storm produced the southern Indiana EF4 tornado that we just viewed in the last video, which killed 11 people with winds estimated at 175 miles an hour, while the second storm produced a much weaker tornado with winds estimated at 110 miles an hour. One reason the second storm, which had an updraft just as strong as the first and produced softball-sized hail, did not produce a similar strength tornado is that the low-level atmosphere below the base of the storms was so drastically altered by the first storm, both in stability of the air as well as the wind field, that the intense rotation could not make its way to the ground. This is one of the reasons that real-time spotter reports are so valuable to the National Weather Service. Doppler radar is a fantastic tool for identifying which storms have the potential to become severe, but they can only tell us what is happening inside the storm, not on the ground below it, which is where we all live. National Weather Service meteorologists must go through years of education and training before they issue their first tornado warning, but you don't need to be a meteorologist to let radar help you keep yourself and your loved ones safe. The most important thing to know is your location on a county map of your area. In this example, a loop of the Doppler radar near Nashville shows storms crossing Tennessee and Kentucky. In addition to showing the location of the storms, this sequence shows several warnings being issued. The bright red boxes that appear are the tornado warnings, while the yellow ones are severe thunderstorm warnings. If you know where you're located relative to the storms on the radar, then you can watch as they move toward you and take safety precautions long before the storm is on top of you. For spotters, radar not only tells you when a storm is heading your way, but provides information about what type of storms are coming, which should help you to better identify the clouds that you see. Providing an accurate cloud report is the best way a spotter can help the National Weather Service in the warning process. Unfortunately, though, knowing where you are on a map relative to an incoming storm may not be enough. Take, for example, this squall line, shown moving toward you on radar. Looking from the position indicated, what might you expect to see looking to the northwest? Unfortunately, if you happen to be in a valley with hills just off to your west, the answer may be little more than dark clouds, since your view is severely limited by the nearby terrain. Quite frankly, this type of report won't be of much help to a warning meteorologist. In this same scenario, let's say that you're not at the bottom of the valley, but still not near the top of a hill or ridge to your west. In this case, your view would look something like this. You say to yourself, whoa, is that a tornado? It looks like a funnel-shaped cloud coming down to the ground. Before you report a tornado, though, let's say you're able to get to the top of the hill and see what's really coming toward you. This horizontal elongated cloud stretching nearly to the horizon ahead of the advancing storm. Based on your spotter training and the radar image that you saw on your computer before looking outside, you recognize the cloud to be what's known as a shelf cloud. Instead of reporting a tornado, you call the National Weather Service to report a shelf cloud, then prepare for the gusty winds that you know will occur as it passes your location. Now let's look at the same storm from a different location, looking parallel along the length of the squall line toward the south-southeast. In this location, you might see something that looks more like this. Your training should help you recognize the dark, turbulent cloud getting ready to pass overhead for what it is, a shelf cloud. The turbulence associated with this cloud is related to the fact that on the leading edge, warm, moist air is being forced upward, causing a low-level cloud to develop, while behind the shelf, precipitation is occurring in the downdraft area. If the downdraft is strong enough, it will spell trouble for this trucker, as intense winds blowing perpendicular to semi-trailers, especially lightly loaded ones, have often proven strong enough to tip over even quickly moving vehicles. Finally, what might you see once the squall line has passed to your east, and you're in the area depicted by red on the radar? Most likely, not much. At least not much in the way of visibility, that is. When you are in the area of heaviest precipitation, you may not be able to see more than 100 yards in any direction. For all intents and purposes, at this point, your storm spotting is over for this storm. But does this necessarily mean you're out of danger? Not hardly. Remember the rain-wrapped squall line tornado that we looked at in the How the Weather Works module? If not, here's a quick refresher to remind you. The tornado occurs at the midpoint between the two main sections of the broken squall line. Remember that squall line tornadoes are the most common type of twister to strike in central Kentucky and southern Indiana. In addition to the problem of them being masked by heavy rain, these tornadoes very frequently don't form visible funnels at all. When combined with the fact that the squall lines that generate these tornadoes often move through after sunset, these tornadoes are dangerous because they offer such little visual evidence of their presence prior to them wreaking their havoc. Now this isn't the tornado that occurred with the squall line in the previous slide, but it's one that developed under similar circumstances. The video here was taken from a security camera in southern Indiana about 4:30 in the morning, when most people were asleep. Watch as the initial rain and gust fronts start 10 to 15 seconds into the clip. Now the wind-driven rain continues for another 60 seconds, which we've sped up here, before we start to see more action. First, a porta potty slides in from the right and tips over. Porta potties are pretty light, though, and it certainly doesn't take a tornado to blow one over. Strong winds continue for about another 30 seconds after the porta potty tips, though, causing more minor damage in the area. What happens next, though, is explosive damage as an EF1 tornado scatters large debris and tosses a 6,000-pound trucking container across the parking lot. This tornado continued for another 3 miles, with wind speeds of 85 to 100 miles per hour, crossing over the Ohio River into northeast Louisville before lifting. No storm spotter training would be complete without a discussion about nature's biggest imposter, the tornado lookalike. We mentioned in our How the Weather Works module that shelf clouds are frequently mistaken for wall clouds, and in some cases even tornadoes. But there's another class of clouds that has also fooled both casual observers and even trained spotters over the years, the Scud Cloud. Scud clouds are ragged, low-hanging, and often detached cloud fragments that can come in a variety of shapes, including apparent funnels. They're formed when very moist air rises near a storm, either near the gust front or near the updraft region of the storm. Their low-hanging location and frequently dark and ragged appearance make them look ominous, especially if they're moving quickly with the outflow of the storm. Movement alone, however, does not make a cloud dangerous. Rotation does. If you're uncertain about a low-hanging or funnel-shaped cloud, watch it for several moments. If there's no rotation, it's probably a harmless Scud cloud. If there is rotation, protect yourself and report it to the National Weather Service as soon as you safely can. If you can, send a short video clip to the email address shown in the lower right-hand corner of these slides. Let's go over a few key elements from this module. The most important feature to look for when storm spotting is rotation. A tornado can be on the ground causing damage, even though no visible funnel is seen connecting it to the parent thunderstorm cloud. Natural and man-made obstacles can hinder your view of low-level cloud features and result in misinterpretation of storms. Poor visibility and heavy rain can hinder identification of dangerous cloud features. Squall line tornadoes are especially difficult to see because they commonly don't have a visible funnel, often occur in an area of wind-driven rain, and frequently occur after dark. Scud clouds are non-rotating clouds that may look like a tornado. Knowing your location on a county map of your area can not only help you protect yourself prior to a storm's arrival, but can help you prepare for what type of clouds you may see. If you're safely able to record rotation in a storm, send your video to lmk.ops@noaa.gov to let warning meteorologists know what you've seen. Congratulations, you've completed Module 3, Storm Spotting. Go to the link below to complete a brief quiz on this module to go on to the next level.